Hello, everybody. It's showtime again. We're going to have a ball here. I'm in a ball. Yes, I'm talking about a ball. Look at the thing. It bounces. Yes. But first of all, before we have a ball and talk about projectile motion, I want to catch up a loose end from the last video. Remember the law of universal gravitation, which says that we're all attracted to each other, all masses, living or non-living, living and non-living, and all the rest. I wanted to talk about this formula again and use the term inverse square law. Inverse square law, which says that the gravitational force is inversely proportional to the square of the distance. Inversely proportional to the square of the distance. This was part of Newton's genius as well. You know, the knucklehead, when he started class, they lined them up, seated them according to their scores, the high score being the first desk and so on. He was in the last desk. Yes, he was to start with, but he quickly moved to the head of the class. Well, just a little tidbit there. Anyway, inverse square law. So what it says is that force is inversely proportional to the square of the distance. Our force is proportional to 1 over d squared. So that means that if you are twice as far away, what is the force? Twice as far away. 1 over 2 squared, 4. If it's 3 times as far away, 1 over 3 squared is 9. It's 9 times. 4 times 1/16 is strong, the force. 5 times 1/25, you get the idea. So for the third question, what is the force if you are 7 times away, as far away? What is the gravitational force if you're 7 times as far away? 1 over 7 squared is, and there's your answer. Very nice. All right, so now we're to today's topic, or the second video's topic, which is projectile motion, which is cool. Anything that is thrown, tossed, kicked is a projectile. And the path of any projectile would be a parabola, a parabolic or curved path. Now, first, this is when I wish that I had a class, but picture this, if you will. I get a paper ball. So, and here it is. I have it for you. And I get another paper ball. And you can see them, and I will pass them around the room, pass them around the TV screen, drop it in there, let you see that they're exactly the same. So picture this, Mr. Banks, Super B, is on top of the lab table. And here's what I'm going to put before you. I want you to visualize, because can't really catch it in here exactly. I'm going to drop this one. And I would have half of the class clap when this one drops. When it hits, that is. Half of them would clap. When this hits the floor, boom, clap. Now this one, on the other hand, this one over here, I'm not going to drop it. I'm going to launch it horizontally. I'm going to throw it horizontally, just as hard as I can. But the trick is, and after years of experiment, I have achieved this. Drop them from exactly the same height. One is dropped and one is launched, like so. Did you catch that? Cool. Now the question is, drop this one, launch that one, which one will land first? And I have my students draw a picture of what the path of this one will look like, and what the path of this one will look like. And then I have them predict. Ball A will hit before ball B. Or ball B, since it's launched horizontally, will hit before ball A. Or, if you're just wild and crazy, say they hit at the same time. So which is it? And why? And that is your fourth question. What is the correct answer for how ball A and ball B land? A first, B first, or they land at the same time? Hint, that is your correct answer. They land at the same time. And there's this classic picture in every physics and physical science book that I've ever seen. It seemed like they would come up with a different one. But it's on page 99. And that depicts what happens when you have one ball dropped and one ball launched horizontally. I believe that is a red ball is dropped and the yellow one is launched horizontally from the same height at the same time. And as you can see, as those lines going across the page, at any given point, they are exactly the same distance from the ground. Both are accelerating vertically due to gravity at negative 9.8, or in our books sometimes uses negative 10 meters per second. Gravity acts equally on the one dropped and on the one launched horizontally. However, because one was launched, and I've made this beautiful. Here we go. Picture for you. Is that not gorgeous? And you can see in the blue, it represents the vertical velocity, and it gets further and further apart for each time interval because gravity is increasing the speed at 10 meters per second. For every second that goes by, the speed increases 10 meters per second. So it gets further and further apart. However, you will see in red that the horizontal velocity does not change. It is constant. So basically, the only thing that stops the horizontal velocity is gravity, because eventually it hits the ground. The horizontal velocity, though, is still exactly the same as it was when it left my hand at the top of that cliff up there. That is, of course, me there at the top that just threw that ball shoom, off the top of the cliff. You got it? Okay, so that's a very interesting concept. Maybe a little hard to wrap your head around. And I've often told my students that I want to go out to the Utah salt flats one time and get me a long-range rifle. I want to stand. I want to shoot that long-range rifle with it perfectly parallel to the ground, and somehow have a mechanism that as soon as I pull the trigger, as soon as I shoot the rifle, a bullet will be dropped from the same height at the same time. Now, what should happen? Well, of course, the bullet dropped and the bullet shot should hit the ground at the same time, because the horizontal velocity does not depend on the vertical velocity. They're totally independent. So if I just sort of nudged it out the end of the barrel, flicked the bullet off the end of the barrel, and dropped another one at the same time, they would hit at the same time. But if I shot it at a much higher horizontal velocity, they would still hit at the same time. Pretty cool, huh? Because gravity acts equally on both of them. The vertical velocity increases at 10 meters per second. the horizontal velocity stays constant. Pretty cool. And you have to take that into account when you're dropping something from an airplane to this or that. Now, there's a couple of formulas that we will use. But first, let's do a couple of 2 or 3 nomenclatures, just naming. Okay, first of all, y, of course, is the height that something is dropped, launched, tossed, kicked from. And x is the range, or the distance from where it was dropped to where it lands. That's the range. Okay? Now, there's 2 formulas, and I notice I put them in color coding. Whoop, whoop, whoop. In red is your formula for constant horizontal velocity, which is simply distance over time, or you could say x over time, of course. And you have 2 formulas for vertical velocity, vertical distance. The first one is distance, or y, is equal to 1/2 gt squared. If you want to know how tall it is, you would say y equals 1/2 times 10 meters per second squared times time squared. Now, on the other hand, if you knew the distance, you knew the height, and you wanted to find the time, you would rearrange the equation. You would have t equals the square root of 2y over g. So those are your 3 formulas for projectile motion. So let us take a moment and look at one of the problems in the book about projectile motion. On page 100, it says, a ball of mass 1 kilogram rolls off a 1.25 meter table. So it rolls off a 1.25 meter table, which would be like y right there. 1.25 meters is y. And it hits the ground 3 meters from the table, which would be x. So, in order to find the time, you would say t equals the square root of 2 times 1.25 divided by 10, which gives you 0.5 seconds. And since you know the distance, or the range, the x, you simply say 3 meters divided by 0.5 seconds gives you 6 meters per second for your horizontal velocity. Nice and simple. Distance divided by the time. The way you found the time is rearrange that equation for vertical displacement, and it's t equals the square root of 2y over g. That's all on page 100 to work out. Now the other problem is about a tennis ball, and you have a net so high, which you know the height of the net, which of course is y, or vertical displacement, and you know x, which is the distance from the net to the end line. And so the question is, how fast will it travel in order to stay in bounds, or to hit the end line? Okay, so it is projected from the top of the net, or passes over the top of the net, and it takes that parabolic path until it hits the end line. So the question is, what is its horizontal velocity? So again, you say square root of 2y, which in this case is, I'm looking at my notes, 1 meter over 10 meters per second squared, gives you, well, it doesn't break it down on this formula. We find that number, and you divide that into 12. So 12 meters divided by the square root of 2 times 1 over 10 meters per second squared gives you a velocity of 27 meters per second, horizontal velocity, which of course is constant. Have we got that? I hope so. So there it is, worked out right there. Right there. You see it? Okay. About 2 columns over from this hand right here. Okay. And then if you will look down there where I marked in the book on page 101, if you read those last 3 or 4 sentences, they will give you hints for your lab about those angles, hints for your lab. Cool. All right, one final thing I wanted to do, or two actually, and if I made it, I've forgotten how many questions I've asked now. Is this the 4th one? I think so. How fast does an object travel in orbit around the Earth? Again, Mr. Genius, Mr. Sir Isaac Newton, was the first person to think about this, a thought experiment he conducted, knowing the curvature of the Earth, and he said, that if you launch a cannonball at 8,000 meters per second, remember that's the horizontal velocity. Okay, there it goes. That's the horizontal velocity, which does not change, which is independent. But as soon as that cannonball is launched at 8,000 meters per second, gravity starts to pull it down towards the Earth. Well, guess what he found? He found that if you drew a tangent line from the Earth and you went out 8,000 meters, like so, a tangent line that was 8,000 meters, this is 8,000 meters, it would fall 4.9 meters, or we round to 5 meters, because gravity is 10 meters per second. And if it falls 5 meters in 8,000 meters horizontal range, and it falls 5 meters down, that means, what does that mean? It means that the cannonball will never hit the ground, because it's going at 8,000 meters per second, and every second it falls 5 meters, it never touches the ground. So the cannonball is in constant free fall around the Earth, like the astronauts we talked about in the earlier video. So 8,000 meters per second is the orbital velocity of a satellite around the Earth, thanks to Sir Isaac Newton back in the 17th century, 1667, 8, 9, 10, 1670, around there, when he wrote Principia Mathematica in 1687. He talked about this. Amazing. We knew the orbital velocity before we ever were able to put anything into orbit, just like we knew the mass of the Earth before we could even see it from space or had seen all the surface of the planet. Wow. Okay, that's it for video. And if I need a 5th question, if I haven't already asked 5, the 5th question is, what is the 5th question? How about this? Who is the coolest physical science teacher on Earth? Mr. Banks, good. Enjoy talking to you. Enjoy this video. Get those labs in. I think you'll enjoy this one. And problems Friday night. Get them enjoying those discussion board questions. I like when you get specific stuff on those projectiles and a very specific satellite, a name of a satellite and what it actually has for velocity and altitude. And of course, your test is due for Chapter 3 on Sunday, and Chapter 4 will be the next Sunday. See you later.